Professor N. Hemachandra from Department of Industrial Engineering and Operation Research, IIT Bombay. His current research interests include operation research methodologies like machine learning, including reinforcement learning and neural networks, learning algorithms, Markov decision models, queuing models, and game theory. Application areas include communication networks, supply and value chains, financial engineering, logistics, power systems, and related resource allocation problems. Let me call upon stage Professor N. Hemachandra.
Good afternoon, everyone. Yeah. So, it's an honor to speak on this occasion, but it's always a challenge. I don't know what type of talk I should give. But anyway, I decided on one variant, which is just a summary of, I think, something like 3 to 4 papers that I have worked over years with a bunch of students. All right. That sort of explains a strange title. Some of it, hopefully, I will be able to convince and do some justice towards the end. All right. There is this idea. There is this idea called congestion. Congestion is prevalent in variety of ways, and any stable queue will have a surplus capacity by definition. The slack of 1 minus rho. So what can one do with that? All right. Okay. So one simple way is that, okay, sell it. So then you say that, okay, what is the price at which you want to sell, and what service levels, SLAs, service level guarantees, one can guarantee for that. So now I started with a single class queue, as I call it. I moved on to 2 class queues now. So this is a bit strange actually, in the sense that multi-class queues analysis and design is quite hard, as opposed to the classical single class queues, which are more prevalent and well understood. One of the reasons is that this is now a joint pricing and scheduling problem, because you have 2 classes, you have to schedule them as well. So yeah, and this part of this work, so this thesis, okay, I think unfortunately it doesn't show up there. Yeah, here is a picture for that. So we have this existing class, what we call as a primary class, and this is what we are now selling it to secondary classes and the single server. I mean, it doesn't matter actually what you do at some level. I won't go into details, the delay dependent priority rules. Yeah. All right. Okay. So here is this is a description. I won't go into many details now, but there is this beautiful idea due to Leonard Kleinrock called delay dependent dynamic priorities. The priority is not class dependent, but it is instantaneous time dependent. The problem turns out to be non-convex constraint problem. It's non-convex both in objective function as well as constraints. What essentially Sudhir pulled off is, we have a finite step algorithm for global optimality. It's a finite step algorithm. Most non-convex problems typically have this local solutions which are iterative. It's quite different below. The result is quite different, and sort of, I personally feel it's an elegant result. It's a finite step algorithm. All right. Okay. So yeah, I mean, many other things were mentioned in this type of activity. We have an insight where exactly is the delay dependent priority has to be used, with range of the with the problem instance parameter space, what instances actually need to use delay dependent priorities rather than the static priorities as optimalities. We can, roughly speaking, if you insist, or if you declare and assure service levels which are very loose, so to speak, we need not do static dynamic priorities, but on the other side, if you do the very short guarantees you are guaranteeing to the incoming customers as part of the SLA, you really need to have dynamic priorities. I mean, these are and many other insights are there. All right. So what is now sort of surprising is the way I mentioned this to you. In fact, the original way we talked about it is, and it's a firm, a survey firm or the queue, which is actually trying to optimally serve, optimally price its services. Surprisingly, this is actually the solution that is there at the optimal prices and optimal schedules are actually equilibrium of a certain model. The model is actually, imagine that this is a queue anyway going on, and this is the secondary class customers. So it's a game, a non-cooperative game between the queue, the facility, and the market or the service, large class of secondary customers. And and what is the Nash equilibrium of this particular game? Is the optimal prices and schedules that are obtained here, this side. This is essentially because we have this linear demand functions which are quite popular here, and that essentially meant that a hard, computing Nash equilibria is known to be very tough. Even in special classes, it is very hard. The structure of the problem essentially gives us the idea, gives us the guarantee that actually whatever is computed is actually Nash equilibria between these two identified players. All right, this is what we meant by and all right. Okay, this is part of Manu's thesis. So sometime back he wrote with us. Yeah, all right. So I mean, essentially we'll continue with the same type of framework, except that slightly look at a more general class of models. View them not as a, earlier we said that there is a queue here, which is basically one can view that as a service facility, and there is a class of customers, secondary class customers we mentioned here. We can talk about a slightly general framework here. There is a service provider, and it can do a variety of operational decisions, usually modeled as Markov decision models or stochastic dynamic programs. And then essentially this part of the problem is actually to think about a service, optimal policies. Optimal policies could be pricing, or it could be operational like scheduling and many other things. The user set is interested in the quality of service. It is analogous to the earlier model that I mentioned here. The secondary class customers are interested in their mean waiting time. They are going to suffer. So sorry. Okay. So this is interested in the quality of service they experience. And the examples are actually in one of these papers is a stylized model for this cycle deployment in the campuses, the vehicle rerouting type of problems, and call drops. This could be the instances for this user set here. Assume that essentially because of the game theoretic interaction between these two agents is we have the revenue optimal decisions by the service provider will imply a quality of service to this user set. The user set feeds an arrival rate, a mean arrival rate, which is dependent on the quality of service it is experiencing. So that is the game theoretic topic I am talking about it. All right. So this is a slightly generic model, and decisions of one as in a game affects others objective function, and we can talk about this as a game here. There are a couple of works in this direction. One of our this is illustration, and okay, maybe I will skip it here. This class of models need not guarantee existence of the equilibrium point. The earlier model that I started off with saying that pricing surplus capacity will have indeed a Nash equilibrium. This class of models need not have it. We have this notion of equilibrium sets, and and essentially the interaction between these two agents toggles between the equilibrium sets. Okay. So here is an illustration for that, for instance of a problem. I mean, these are not very important, that illustration, but certain parameter space can be partitioned into essentially three halves. The left half, if the interaction is about 1 point in the left half of this parameter space, the best responses would be into the other right half of the space, loosely speaking. I didn't draw it. There is a symmetric thing we can think about it. All right. The middle portion is where any interaction coming from this parameter arrival rate in the middle portion will sort of pull you back into either of these right half of the region or the left half of the region, what we call equilibrium sets now. Fine. I just drew one particular instances. Right. I hope I'm clear. By the way, just feel free to interrupt me and ask for any clarification. That would be more better than me going in one direction. All right. So this union of this left portion and the right portion is what we call equilibrium set, and the middle portion is what we call repelling set. All right. Yeah. Okay. So yeah, one of the things is that one of the insights we have is that this could be one explanation why there are business cycles in the service systems. The business cycles are typically of a period of high regime, high mean demand, followed by low mean demand and high mean demand. This illustration is like that. We have a high mean arrival rate here, which is pulled into a low mean arrival rate, and vice versa. So these business cycles, that is one explanation for this, why these business cycles exist or people see in the service systems. All right. Okay. So yeah. In terms of the time, all right. I think I still have a lot of time. Yeah. Okay. All right. Yeah. So all right. Yeah. Okay. So why one can dig into some details. Actually, what triggers, so to speak, this type of phenomenon of a repelling set and an equilibrium set. It is essentially existence of multiple revenue optimal policies. What the service provider is actually working with a certain objective function, and there is revenue optimal policy, and it can be then, depending upon the parameter space that you have, the model can have multiple revenue optimal policies, and that will actually what you are plotting here, if you can see, is actually hope you are visible here. So this is the quality of service basically. The policies are revenue optimal, but they yield different service levels, and that creates this discontinuity, and this discontinuity in turn creates this toggling that you are mentioning. So this is one instance of one explanation for this, why these multiple revenue optimal policies will lead to this type of equilibrium sets, and in particular absence of equilibrium points. This is primarily done as a MTech thesis of Kishore and master's thesis IEOR of Sandhya, and later on it appeared in as a journal paper. All right. Let me go into some more details here. I mentioned about sort of slightly what should I say, sort of contradictory terms. There is a discontinuity here, but we are talking about a continuity over a range. So the thing is, some explanation actually why this discontinuity points are actually few in number, quote unquote, informally speaking. This, if is just recall that actually this is a model of this original model that I mentioned here is modeled that as a MDP here, a sequence of decisions being made here. So there is this beautiful idea under mild conditions, an MDP has an equivalent representation as a linear program. Somehow this is, I somehow feel that this should be widely popular in some sense. Somehow it is not that popular. It is actually a representation, one-to-one mapping. MDP is equivalent to a linear program. Now, we piggyback on this result and existing result, and there is a bunch and beautiful work on the parametric continuity of linear programs, which will yield, because of this representation, that we are doing a parametric continuity of the MDPs and associated continuous functions. So that is the way we approached. We approached this result, that there is a range of continuity, there is a discontinuity, and there can be another range of continuity. Right. So this parametric continuity of LPs is actually piecewise continuity. This is due to the original work I know of. This is due to George Danjing, John Folkman, and Norman Shapiro. And there is a nice summary of this and related extra results by Roger Wetz in this sort of cute short paper, relatively cute short paper. This is originally done as a part of MTech thesis of Rajesh and Muhammad Kavi, and later on we sort of followed it up in a certain sense. Right. Okay. Okay. So, okay, maybe just give me a minute. All right. These pieces of work are more of model and given model and its analysis and insights out of it. Yeah, one can talk about a data-driven versions of it. Then it will naturally relate to this reinforcement learning type of framework. Yeah, the general observations I think in the community is that learning in games is hard, really hard conceptually as well as computer. I mean, yeah, it's more of conceptually really hard in general. A decentralized versions still with independent agents can be pulled off. This part of is actually last year's PhD thesis of Prashant, where one can argue that actually in the decentralized setup, decision making and decision making can be learned, so to speak. All right. Okay. So yeah, what can one do more? This is one can do more in this direction. Okay. So let me go back to this picture. One can ask a question: can one, given a set of data in a data-driven way, one can predict whether a certain instance will have an equilibrium point or an equilibrium set. That will boil down to the way I am talking about it, predicting a certain discontinuity of a certain nature and a discontinuity of a certain function. So these lead to two types of problems. One is the functional data analysis, where you are trying to predict a certain function or a variant of that. And the other question is in existence of a equilibrium, discontinuity of a certain nature or not is a binary classification type of problems. So in one direction it can go into this type of set of directions, and in another direction it can go into the functional data analysis type of problems. All right. Okay. So probably, yeah. Okay. So yeah, here are some comments in terms of my time. I suppose I have a couple of minutes. So yeah, here are some my comments which probably some of you may be interested in and can be potentially can be controversial, but nonetheless this is my view. So over years I found that this IEOR has a rich bouquet of opportunities. I think somebody mentioned in earlier also, we don't own a technology in the formal sense, in the way the technology word is used or interpreted. For example, we don't own a steel making technology in some sense. IEOR doesn't own, or it doesn't own certain concrete making or whatever it is, some technology, or even chip making, VLSI. But it has its own unique notions. For example, this notion of optimality is a core IEOR notion. And the idea of a policy, a sequence of decisions in multi-stage problems is actually, yeah, these are all various notions one can think about it. Scheduling, sequencing, idea of a flow. We talk about a flow in systems. The classical IE part is actually like that, flows and stocks. And yeah, the very beginning I mentioned that there is a stable queue and it has surplus capacity. There is an instance of a slack. The stable queue has a slack. Rephrasing the original question is actually, what can you do with the slack? The ideas of a slack that is available in a certain instance or resource, and flow balances. The best of this results in this flow balance standard results as so-called classical Little's law, and the notions of tardiness, algorithms. These are some notions actually which IEOR, in my view, actually just owns it. We don't own a technology, but we own a lot of notions. All right. Okay. So these are some comments, and here is another 5 comments. Yeah, many of you might have heard about this brilliant statistician called John Tukey. So with the apologies to him, in the context of statistics and its role in natural sciences and physical sciences, he has a nice quote. Basically, he says that any science area is a backyard of a statistician. So with apologies to John Tukey, yeah, my view is actually an IEOR person can get to play in the backyard of any engineer. We run, we build engineering systems, technology systems, we run engineering systems. And with due apologies to John Tukey, this is my take. All right? Okay, thank you. Thank you for patiently listening. All right. So any comments or criticisms, most welcome.
If you have any question, you can ask.
All right. One of my former teachers reminded me of saying something in this direction. If there are no questions after a talk, it means only 2 things. Either everybody understood everything, most unlikely, nobody understood nothing. Anyway, so thank you for patiently listening.